In this session, we're going to be looking at different mechanisms of sorting a list out or an array out. Now, if you remember the last session, we looked at linear search and binary search. And one of the stipulations for a binary search is that the list has to be sorted. So these two mechanisms allow that list to be sorted, and then you can probably conduct a binary search with it. There are multiple mechanisms of sorting data out. For example, merge sort, heap sort, quick sort. But for the purposes of our syllabus, we're only going to be looking at two particular ones, and they are bubble sort and insertion sort. And you may remember bubble sort from year 12. We looked at the algorithm for that at that particular point in time. We're going to be reviewing that, and then we're going to be introducing a new algorithm which is called insertion sort. In addition, we're going to be looking at big O notation in a bit more depth, because we need to show an understanding that different algorithms which perform the same task, for example, sorting algorithms or searching algorithms, can be compared by using criteria such as time and space, the time it takes to get to a solution and the memory requirements. And big O notation is one established mechanism of comparing these algorithms. So we're going to be looking at that today as well. So we've got a lot to get through. So let's begin by looking at some key terms. Let's start with bubble sort and insertion sort. So bubble sort is a method of sorting data in an array into alphabetical or numerical order by comparing adjacent values and swapping them if they're in the wrong order. Insertion sort, on the other hand, is also a method of sorting data in an array into alphabetical or numerical order, but by placing each item in turn in the correct position in a sorted list. So you just simply move it around to the right place. And finally, you should remember big O notation from last session, a mathematical notation used to describe the performance or complexity of an algorithm. And we're going to be studying this in a bit more depth today. Let's begin by looking at bubble sort. You can see bubble sort happening in the top right-hand corner of your screen. The bubble sort is a simple sorting algorithm that works by repeatedly stepping through the list that needs to be sorted and comparing each pair and then swapping them if they're in the wrong order. The pass through the list is repeated until no swaps are needed, which means that the list is already sorted. This algorithm gets its name from the way larger numbers or larger elements bubble to the top of the list. So you can see that the bigger numbers are being gathered towards the right-hand side of the list. Now, this is a very slow way of sorting data, and it's rarely used in industry. There are much faster sorting algorithms out there, such as quicksort or the heap sort. But for the purposes of our exam and our syllabus, we just need to know how to do it because it's one of the most simplest ones to code. So we're going to be looking at this particular algorithm in a bit more depth. Now, on screen, you'll see the pseudocode for a bubble sort algorithm. You've got the identifiers which explain what everything is. We keep to the same structure as the linear search and the binary search to make sure that we obtain the maximum amount of marks in the exam. So we start by declaring an array, we then declare the lower and upper bounds, we declare the index, we declare a flag called swap, which helps us identify whether a swap has occurred or not. This is very useful to finish the process. If no swaps occur, then the list is sorted. Then we have a temporary variable to store the values and a variable called top, which indicates the top of the list, and this should be decreased every iteration because the rightmost item will be sorted out in a bubble sort because everything bubbles towards the right in our case. Then we initialize the upper and lower bounds. Accordingly, lower bound is the value 0, upper bound is 8 in this case. And we start with initializing top and making sure it's the same as the upper bound of this array because the list hasn't been sorted yet. We haven't started comparing things yet. We then have the same structure of loop, repeat until for ease of use. We're going to repeat this code until there are no more swaps. So that means not swap, or the top equals 0. So that means that top, which begins with the upper bound 8, is reduced to the lower bound 0. So that means we've compared everything and there's nothing more left to compare. We start with a for loop and we start the index from the lower bound, which is 0s, to top minus 1 because we don't want to get the final value to be compared to the value next to it. You'll see what I mean in a moment. We set the swap flag to false because at the moment there are no swaps as far as we know. This could be sorted in the first place. We then check if the list at the current index, which is going to be starting with 0, index 0, is greater than my list index plus 1. So that means 0 plus 1. So you compare the value at index 0 with the value at index 1. This is the reason why top has to be minus 1, because when you get to the last value in the for loop, you can't have 8 plus 1, 9. because there is no 9 in the index. That could lead to a logic error. Therefore, top -1 is essential in the for loop, because this helps you avoid the index out of range type errors. Now, once we do this particular comparison and we find that the value in index 0 is greater than the value that's at index 1, then we need to do our swap. So in the temporary variable, we move the value which is in index position 0. Then in index position 0, we move the value which is in index position 1. Then in index position 1, we move the value that is now stored in temp. So we use temp as a temporary storage place to help us move the values around. And we set the swap to true. We then go back to the next index. Now we're going to position number 2. We compare 2 with 3. We do the same thing again, then 3 with 4, and 4 with 5, and 5 with 6, and 6 with 7, and 7 with 8. And that's where we stop, because we've just gone through the first cycle of swaps. We then exit out of the loop and we reduce the value of top by -1, because we now know that the 8th value is sorted. So we're going to go to 7, then 6, then 5. We start decrementing the comparisons one by one, and then we go through the loop again, reduce the value of top, go through it again until the value of swap ends up being false, or we reach top equals to 0, which is the lower bound. So do pause the video and try to understand the logic of the pseudocode. You might also want to try coding this, because that will give you a deeper grasp of how the pseudocode and the algorithm actually works. Now on screen, you can see a possible implementation of bubble sort using Python. You've got the mylist array. We are using a while loop this time because there is, of course, no repeat until in Python. So we can only either use a for loop or a while, and that's there. And it takes you through the list. It reduces the top. All of that's there for you. So you might want to code this in and then see what the results are. That mylist array, which is not sorted at the top, should be printed out as a sorted array by the end of this. Okay, let's move on to insertion sort. Now, insertion sort is another method of sorting a list. On the top right of your screen, you can see it in action. In this method, we compare each number in turn with the numbers before it in the list, and we then insert it into the correct position. So the original list in the top right hand corner is 6, 10, 22, 18, 31, 7, 29, and so on. So we start with the second number, 10, and compare it to all the previous numbers. Now at the moment there's only one number before it, and it's less than 10, so there's no change in the order needed. We now compare the third number, and we compare it with the second one, and we find that's bigger than that, so we keep it where it is. But the fourth number, 18, is less than 22. So that means we need to insert it before 22, but we will also have to compare it with 10 to make sure it's not smaller than 10. So you end up doing two comparisons and then insertion in this particular case. And this process is repeated until the last number is inserted in the correct position and the list is sorted. Now this is a lot more faster at times than bubble sort, but it's still not the most efficient way of sorting. That's where other algorithms like quick sort or quick tree or heap sort can come into play. However, this is again very simple to code. Now on screen you see the pseudocode behind insertion sort. You've got the identifier table which lists what all the identifiers mean, and we're going to keep to the same structure as the previous one as much as possible. So we declare our array, we declare upper and lower bounds, we declare an index, we declare a key which is an integer, and then we declare a place which is an integer value where we can do our swaps in a way. Upper bound is assigned to 8 in this case, lower bound to 0 as usual, top of the list, bottom of the list, and we now use a for loop where we say start the index from the lower bound plus 1, because we don't want to compare the first item with the previous item, which doesn't actually exist because there's nothing before the first item, but we want to compare the second item to the first one. So we start with lower bound plus 1 to upper bound, which is the inverse of what was happening with the bubble sort algorithm, where we were reducing the right hand side by 1. Here we're looking at adding to the lower bound to go towards the upper bound. So the key becomes the second value rather than the first one, because it's lower bound plus 1. So key contains the second value and the place contains the index of the first value. So it doesn't contain the value itself, it contains the index of that value, so that position. So key actually holds the value, whereas place will contain the position, the first position, in this case 0. We then compare the value that's in position 0 with the value that's been held in the key. And if it's greater, then we conduct a while loop where we swap the data if the conditions are met. And the conditions are that the place value has to be greater than or equal to the lower bound, because we don't want it to be below it, because you can't go below the lower bound. And the value that's stored at that particular place index is greater than what's in the key. And this allows us to check each place, and then using the temp variable and manipulations of the indexes and the place, swap values and insert it in the correct place. And at the end of that, we just decrease the place value by -1. And outside the loop, we insert the key at place +1, so we make sure that it's inserted into the correct place in the list. Now, key holds the value that is at the current index of the for loops. So after this, the loop is updated to the next index, and we continue the process all over again. And we keep repeating this until all the items are sorted out. Now, do pause the video and study this algorithm carefully. Try to code this in Python as well, because you know what's coming up next. It's going to be the Python code. So you might want to compare your version with the one that I'm about to show you. But before that, I'm just going to show you a list of numbers. If you have the original list as 20, 47, 12, 53, and so on, then these are the steps an insertion sort will take to arrive to a sorted list at the end. If you are coding in Python, you could probably display your steps as well, just to see whether it matches this, because if you got your logic incorrectly, then it's very difficult for you to test your algorithm, because you'll eventually end up with a sorted list anyway, but you don't know the steps it took to get to that particular level. However, if your logic is correct, this is what you should be getting. So as promised, on screen is one implementation of an insertion sort. This one uses a for loop, it uses a selection and a while loop. It's in line with the pseudocode that we had earlier. Hopefully your implementation is something similar to this. If you haven't implemented it, do pause the video and try to see if you can implement this piece of code, and then with perhaps your own array, try to see if you can sort it out. So why do we want to use insertion sort? What are the benefits of that? Well, insertion sort is very simple to code. It has very good performance with small lists. Now, how small is small actually depends on the power of the computer it's running on, because for a mobile phone, perhaps a few thousand would be a simple list, whereas with a supercomputer, billions and billions of items on a list might be small. It's very good when the list is almost sorted. In this case, very few compares need to be done. The worst case is when the list is in reverse order. That requires a huge amount of swaps. Insertion sort is sort stable, which means it keeps the relative positions of all the elements intact, so it's only just inserting values depending on the direction of travel. It's very memory efficient. It only needs one extra storage location to make room for moving items. It's good with sequential data that is being read in one at a time, for example, tapes, hard disk drives, and so on. Of course, there are disadvantages, and one of the major ones is that it has very poor performance with large lists. And also, if the list is in reverse order, it struggles. So those two are the major disadvantages that are there. And why do we need to look at advantages and disadvantages? Well, because you're not going to be running every type of algorithm when you are conducting a search. You will need to make a choice. So when we compare bubble versus insertion sort, as you can see on the graph on screen, that as the number of elements in the list increase, bubble sort's time increases as well. Insertion sort is still okay, but there are other better algorithms like quicksort, which might have a much more faster performance in finding items in a list. Big O notation is a simplified mechanism of measuring how efficient an algorithm's performance is. And it focuses on the complexity of the algorithm in terms of the input size. For example, if a list has n elements, therefore you might have some relationship to n in how the algorithm operates. It's machine independent, so it doesn't actually matter whether you put a supercomputer or a small Chromebook. You can still work out the efficiency of the algorithm without taking into account processing speeds. It uses basic computer steps, which are very simple once you get to know how they work. And the use of time and space is critical, like how fast an algorithm perhaps can go through a set of elements in a list and what impact that has on the memory requirement. Now, Big O notation focuses on the worst case scenario. Of course, algorithms could have a best case scenario. If an algorithm is almost sorted, then certain algorithms won't take that much time or memory to process that list. Or it could have an average case scenario or a worst case scenario. For example, you could have a list which is reversed and an algorithm takes a lot longer to get it sorted. So the rules in big O notation are that we ignore any constants and certain terms dominate others. On the bottom of the screen, you can see how the order is. Big O of 1 is the fastest, and big O of n factorial is like throwing cards up in the air and hoping they land in the correct order, is big O of n factorial. And everything else falls in between. Perhaps this graph illustrates it much more effectively. You can see the top left-hand corner, big O of n factorial. As the number of elements increase, so does the time. And the best algorithms, the most efficient algorithms, are those that are big O to the 1 or big O log n. A linear search is O to the n because it checks every element in the list, and binary search is big O to log n. Then you got the sorting algorithms, big O of log n, big O of n squared, and then the factorial ones, which take almost forever to sort out bigger lists. So how is big O worked out? Well, we start off with constant time, which means that the algorithm will take the same amount of time every time it's run. In this particular case, the expression x will still take the same memory, the same amount of time every time we execute it. So a simple expression statement is big O of 1. You will always get the answer in the same amount of time. It's constant. Now, it doesn't matter if you have multiple big O of 1 statements. So if you look at this sequence of code, you work out x, which takes big O of 1. You work out y, which takes big O of 1 because there's only one statement. And then you got print x plus y, which adds those two numbers up. And again, this will also give you big O of 1. So once you look at the three total times, it's actually big O of 1 plus big O of 1 plus big O of 1, which is equal to 3 times big O of 1. And if we go with our rules, we ignore the constant, which in this case is 3. So the entire algorithm is big O of 1. Now this simplifies our comparison factor. Of course, you could have big O of 1 plus 10 million. But as the number of lines increase, the base complexity is still going to be big O of 1 because every line will just be executed in constant time because there's no n number of elements involved in that particular line. When we do get the n number of elements involved, for example, in this case, a for loop for x in the range start from 0 and you have n elements, and all you're doing is printing x out, which could be the index in this particular loop. The printing out of the index is going to happen in constant time because all it takes is one clock cycle or whatever for it to be outputted. But depending on the number of elements involved, you can either run this loop for just one element or a million element or a billion element, and the time of execution will change. So the complexity of this one is going to be n times big O to the 1, which means it's big O to the n. And this is called linear time. The time increases as the number of elements increase. And if you look at this example on screen, you've got the first line, which is a simple expression. So that has a big O of 1. And then you've got a for loop, which runs for n elements. So that's got the big O of n. Now, in this case, the total time is big O of 1 plus big O of n. And as we know, the bigger term dominates. So we ignore the O of 1 and we keep the big O of n as the overall notation of this algorithm. And of course, you can do the same thing for quadratic time. In this case, you've got big O of n squared. Basically, that means a loop within a loop. So you've got a nested for loop. First, x is in the range of n elements, and then within that, you have another for loop which runs for y in the range of n elements again, and you're just printing out x times y. So for every x, you're going to go through n elements, so it's n squared. So once again, if you look at the following algorithm, x is an expression which has the big O of 1. Then you print out x in the range of n elements that has a big O of n. And then you've got a nested for loop which has the big O of n squared. If you combine all of these, the total becomes O1 plus big O of n plus big O of n squared. And as we know with the big O rules, the smaller terms are discarded and the complexity becomes big O of n squared. Now it's very easy for us using this particular system to compare algorithms. We just look at the biggest complexity and discard everything else. Let's put this knowledge to the test. On screen, you can see some selections which in comments have been given a big O notation. What do you think the complexity of this algorithm would be? Okay, now all of that was just to make you understand how big O notation is worked out. You don't really need to know that for the syllabus. What you do need to know is that big O impacts time and space complexity. What does that mean? Well, for a big O of 1, which describes an algorithm that always takes the same time to perform the task, an example would be deciding if a number is even or odd. The algorithm will easily work that one out. Big O of n normally describes an algorithm where the time to perform the task will grow linearly in direct proportion to the number of elements, and a linear search is a great example of this. Big O of n squared describes an algorithm where the time to perform the task will grow linearly in direct proportion to the square of n, and a bubble sort and insertion sort are good examples of that. Big O 2 to the power of n describes an algorithm where the time to perform the task doubles every time the algorithm uses an extra item of data, and calculation of Fibonacci numbers, for example, using recursion, would probably fall into this bracket. So that's like a really worse type of algorithm where you add an extra item and the time just doubles. And finally, you got big O to log n, which describes an algorithm where the time to perform the task goes up linearly as the number of items go up exponentially. And that's a very good algorithm. Normally, a binary search is a great example of this. So be comfortable with how the various different types of big O algorithms operate time-wise. But they also operate in order of space complexity as well, because it's not just about how quickly they arrive to an answer, it's also about how much memory they take. You will probably have worked out that it's a similar correlation. A big O of 1 describes an algorithm that always uses the same space to perform a task, and a big O of n describes an algorithm where the space to perform the task grows linearly in direct proportion to n, which is the number of items it's using. And similarly, when you have n squared, it's linear growth in direct proportion to n squared. And the same applies to the rest of them. Normally, you could give the same examples. However, if you wanted to look at specific ones, any algorithm that just uses variables would be big O of 1. Any algorithm that uses arrays will probably be big O of n. And that's all for us for today. Hopefully you understand what is meant by big O notation. You can describe big O notation in terms of both time and space complexity. You can give some examples of common algorithms related to different big O notations. And you can justify how they simplify the comparisons of algorithms by just focusing on the worst case scenario and discarding any other constants or lower values in preference to the highest order value that is possible in an algorithm. You should also be able to implement a bubble sort and an insertion sort. So if you've forgotten about these, do go back and have a look at these two vital algorithms. That's all for this particular lesson. If you do have any questions, please do get back to me. Otherwise, I'll see you in the next one.